Today what we want to talk about is intermediate motors, we're going to call it that, and it's a look at the construction of above ground motors and how to start motors. All right, we'll start out by looking at this picture here, and I've set two motors side by side. The one there is a C-phase motor, the other one is considered what's called a square flanged motor. Okay? I want you to know Stay-Right has been using square flanged motors since its conception. A lot of companies use the C-phase motors. We're going to talk a little bit about what the difference is in them, all right? You'll notice, first of all, that what I'm showing you is considered to be the bottom of the motor, which is where the seam is. So that way, if you've got the seam there, it's a little less likely you're going to get water in there. You'll also notice that besides the seam, we've also got some vents. Now, the vents that are towards the bottom of the motor, is it sitting up like that? Those are your exit vents. The vents that are closer to the shaft are your entrance vents. Okay? This is considered to be something called an open drip-proof motor, because if you were to set this motor up the way that it's supposed to be, those vents would be on the bottom. And any water dripping down on the motor would drip around it and not get pulled into the vents. That's the whole purpose of it, all right? Of course, the other thing you have to be concerned about is if you put this motor someplace where there's leaves or something like that, and those leaves could get pulled up into it. If those leaves get pulled up into it, then you're going to prevent some of the ventilation, and that, of course, is going to make that motor heat up. All right, the next thing we want to look at on these motors is going to be how they connect to the either adapter or pump body volute case, all right? You'll notice the C-flange motor or C-phase motor has those squares that are added to it. Now, those are drilled and tapped. Drilled and tapped. What that means is you're going to put your adapter on the top of that, and then you're going to bolt your adapter down into these bolts. There's actually four of them. You can't see the one on the other side, but there's actually four of them there, all right? If you look in the square flange motor, you can see those holes there. Those holes are just drilled, which means they're bigger than the bolt that's going to go in them, so that way you can slide the bolt through without having to actually thread it through there, all right? If you also look carefully, you can see that we've got an area right here that, and you can't see it on the square flange motor, but it's on the square flange motor too. This is called a water slinger. A water slinger. It's a piece of rubber that fits very tightly around the shaft. It fits so tightly that should the mechanical see a leak, the water would hit that water slinger, and then of course it's called a water slinger because it slings or throws the water off away from the shaft. So that way it can't go through the hole that the shaft is coming out of and get into the bearings. Without that water slinger there, that's what would happen. The water would go into the bearings. If the bearings didn't cause the failure, the water would go through the bearings and wind up hitting the motor and you short it out. One way or the other, you're going to lose at least part of the motor, if not all the motor. If the bearings go bad, the good news is you can just change the bearings out. If the water goes all the way through the bearings and it hits that armature in there, then you're going to wind up losing the whole motor because you'll short it right out. Okay? Now, let's talk a little bit about how you put a motor together. All right? This is called a lamination. Laminations are 1/64 of an inch thick, and you stack them up. You'll notice if you look at this lamination here, I put a square box around the openings there so you can see that there are slots. These are slotted. And what we're going to do is we are going to stack these up. And again, horsepower is going to be based on the length of the core and the size of the wire. We might wind up saying that again later on, but it's important you understand that. Horsepower is based on length of core and size of the wire. So we're going to stack them up based on how much horsepower we want out of this motor. And then what we're going to do is we're going to put a slot liner in each one of those slots. Then we'll go ahead and we'll fill those slots with copper wire. It's called a mag wire. It's got a solid copper wire with a varnished coating on it. All right? So we put that mag wire in there, And then after we get the mag wire in there, what we're going to do is we're going to put a insulator on top. So that wire is insulated all the way around. All right? Then you can see we put some string on there. That's because there is actually some vibration as that electricity moves through there. Remember what electricity is. It's that electron bouncing back and forth. And so because that electron is bouncing back and forth, what we're seeing here is we've got to actually tie these down because they are going to vibrate a little bit. So this is what it actually looks like in real life. And again, if you look right in here, inside that motor, you can see there's the insulator and there's the insulator on top and on the bottom. Okay? We call it Mylar. It's a plastic type insulator, and it prevents the flow of electricity. So that way the electricity has to go through the coils and can't touch the core. If even one wire touches that core, it shorts out. So we can't allow that to happen. All right? And then again, you'll notice up here, we've got it all stitched together. There's actually a start winding here and two run windings. This is an above ground motor. So there's a start winding and two main windings with these motors. Once we get what we call the stator built up, so we start out with a lamination, then we go to a core. Once we put the wires in there, we call it a stator. Once you get the stator assembly built, the next thing we're going to do is we're going to put our rotor assembly in there, and now we have a motor. All right? When you take a look at how the rotor assembly gets built, and once again what you're going to see here is the rotor assembly, the lamination for the rotor is the inside of the lamination for the stator. And so when they punch out these laminations, they're getting an inside and outside one at the same time. All right? You'll notice, though, that while the outside one had slots in it, the inside one just has a hole. Okay? Whatever shape that hole takes, these are taking a teardrop shape, but it still has a hole in it. And once again, what we're going to do is we're going to stack those up. Once we get them stacked up, then they're going to go into a machine that is going to push aluminum, hot aluminum through there. Okay? And now we're going to wind up with the rotor. To make the rotor assembly, while the rotor is still hot, we're going to take that rotor and we're going to put it over a shaft. And of course, there's a jig that it goes through, so the shaft is in the exact same place on all of the rotors. All right? Then we're going to add to that the bearings and the fan. Now, it's very important, and this is one of the things that I need to hit on here. When you want to take the impeller off of this pump, it's very important that you do not put a screwdriver in that fan blade and try and hold it that way. If you look at the very shaft of the motor, the very back of the motor there, the very back of the shaft, you'll see that it's squared off. That's a 7/16 split it fit there, and that's so you can take a 7/16 wrench in the control area of the motor and hold that shaft in place. Some guys like to because it's easier, take a screwdriver and stick it up through the vent area in the front, and once again, now when that happens, you wind up breaking off some of those blades, and once you break off those plastic blades, now you're not going to get the ventilation that you need. So it's very important that we don't do that. You'll notice the other end of the shaft here, the front end of the shaft, is threaded, and again, depending on the impeller that we're using, it could be threaded, it could be keyed, but there's going to be a way to attach the impeller to that shaft. All right, so right there we're going to attach it. This is a look at the back of the motor. The motors that we're using currently are called A.O. Smith. Now, for those of you that don't realize it yet, A.O. Smith was sold. They are now owned by Regal Beloit, and so slowly but surely they're changing the name to Regal Beloit. They may just be calling it Regal. These motors have a two-compartment to them. Even your older GE motors also had a two-compartment to them. Okay, the compartment that housed the stator and rotor assembly and then this compartment here, which is your control assembly area. And so we're going to take a look at all those controls that are in there. We'll start out with the capacitor. This is a look at a real capacitor here, and of course you're going to notice that two yellow wires get hooked up here, and over here there's two spades but only one wire, and it's a white wire with a black or a red tracer on it. All right? But I do want to make note that these are U-shaped spades. The reason this is important is because of how the electricity is going to go through that motor, or through that capacitor. So what happens is we put a yellow wire here, we put a yellow wire there, and then we put the red and white wire here. If you look at it from the side, it's going to look like this. We'll hook our wires up there. One of the yellow wires comes from the overload protector. It's a thermal overload protector. We'll take a look at that in a little bit. And one of those wires comes from there. That wire goes into the spade, and then remember, it's a U-shaped spade. That current can go right through the spade and right down that other yellow wire. That other yellow wire goes to the first of the two main coils in the motor. So it's going down to the motor. All right? The red and white wire is going to go over to the switch. Now, of course, you'll notice the current going down the red and white wire has to go through the capacitor first. The purpose of the capacitor, as the current goes through there, it's going to boost that current that goes down through that switch. So what's going to happen is it's going to go down in there, and then as the current comes back up, it boosts that current coming back up. So I could put in a running capacitor, I might put a half an amp in and get 2, 2.5, maybe 3 amps out. So it's a way of boosting the current. With a starting capacitor, you get even more than that. And that's why starting capacitors can only stay in play for a very short period of time. Because if you leave them in play for too long, the current going down through that switch becomes too high, and you burn up your starting coils. All right? So that's your capacitor. Now, the capacitor has to be taken out of play, and to do that, we use two parts. One is called the governor. The other is called the switch. Now, again, I do want to point something out about this particular picture. This is an older picture, and so this is an older switch. They redesigned that switch about 8 years ago, and it doesn't look anything quite like this. They did it for a very important reason. The reason was people were breaking switches when they were trying to test them because they weren't doing it properly. So they redesigned that switch so you can't do what you used to have to do. They used to say, stick a heavy piece of paper between the points, and so you'd either push down on the white dot in the middle there, or you'd lift up on that one where the points end up at. And then, of course, you'd bend one or the other, and you either have a permanently closed or permanently open switch, and it wouldn't work. And then, of course, people would want warranty on it, so it's like, we're going to fix this, but it doesn't happen anymore. All right? So this is what the current switch looks like. And you can see here by looking at it, there's a governor underneath it. The governor has two springs on it there. You can see those two springs. Those two springs are compressing and pulling in and holding closed what's called the counterweight. And so if I take the thing apart here and we look just at the counterweight, there's the counterweight right there, and this tip of the counterweight right here, when the pump is off and those springs compress and close, they pull that tip and push up on that tip. Now what that tip's going to do is it's going to push on a little white plastic piece that connects it to the bottom piece of the switch. All right? And of course, as it does that, then it's going to push up and it's going to close those points. So right now, what you're looking at, where those 2 points come together, they're right at the end of each of those pieces of copper. There's points there, and they are closed. This is a normally closed switch. Okay? So when we look at the switch, on the left-hand side, you'll see the switch is closed. It doesn't look like it, but it really is. On the right-hand side, that switch is open. All right? And it is the job of the governor to open that switch back up. There is a little bit of bend in that bottom one, and it wants to push down. And again, we've got that little plastic white piece underneath this, that bottom point there, and that's riding on top of that governor. So what happens is, when the governor gets up to speed, now let's talk about up to speed, all right? So this is the switch here. You can see the one on the left-hand side is the bottom one. The one on the right-hand side is going to be the top one. And the top one doesn't have any spring in it, but the bottom one does. You'll also notice, and again, this is not anything that has to be a certain way. You'll see on this particular switch that the red and white wire is hooked up to the left-hand side, the red wire is hooked up to the right-hand side. All right? It is a normally closed switch, so it really doesn't matter which wire gets hooked up where. The red and white wire, remember, comes from the capacitor. The red wire goes down to the start windings in the motor. All right? If we flip this over, so here's the front side of it, top side of it, there's the bottom side of it. And what I want you to notice is those rivets. All right? That's one rivet there. By the way, that's the same rivet. You're just looking at the opposite side of it. Here's the other rivet here. And, of course, you notice that those rivets not only are holding the strips in place, but you'll see there's also spades there, and those wires get plugged into the spades. When you do your testing, it is imperative that you take your ohm meter and clip your alligator clips on those spades, because that's how you get the best reading. So don't touch the top of the rivet. Get actually down there on the bottom side of it where those spades are and clip your alligator clips on those spades. All right? We'll talk more about that in the next one. All right? This is how the switch works. Remember, it's two parts. It's the switch and the governor. All right? You'll notice that it shows you there, and they're actually on the opposite side now. Now the red and white wire would be on the right-hand side, and the red wire is on the left-hand side. If you were to look at it in the off position, you can see that the counterweight is pushing up on that plastic piece, which is holding those points together. Now, when we get up to 70% of the running speed, about 0.3 of a second, all right, so 70% of 3450 RPMs is about 2,415 RPMs. That's when the governor, the counterweight on the governor, the centrifugal force is so great that the spring can no longer hold it, and the governor pops out. The counterweight pops out. As the counterweight pops out, it drops down. As it drops down, it allows the spring that's in that bottom piece to push down, and that opens up those points. And that's what we were looking at earlier, is the points being open. Okay? When the pump turns back off, those points close back up, and now we're back in a normally closed position again, so we can start the motor the next time. All right? The next piece we're going to look at here is called the overload protector. Some people call it a thermal overload protector because it's measuring temperature. All right? You can see there's three hookups there. If you actually look at them, you can see they're numbered. Number one, now you'll notice number one has the light blue wire on it. It's going to go over to the terminal board. Number two has the white and black wire on it. That also is going to go over the terminal board. And number three, that's got the yellow wire that's going to go down to the capacitor and gives the power to the capacitor. All right? If we open this up, I want to go back just a second. I'm sorry. I want to go back just a little bit. You'll notice that little nut in the middle. There actually is a plastic coating over it, because the only way for you to do anything with that nut is to take the plastic coating off. And if you take the plastic coating off, guess what you do? Void the warranty. So that's why they put that plastic coating on there, to make sure nobody's messing with their overload protector. All right? So we turn it upside down, we go ahead and take it off there, and we take it apart. And when you take it apart, you'll see there's two basic parts here. All right? You're going to notice that this point connects to that point, and that point connects to that point. Okay? That little screw device in the middle holds it in place, and make sure that those points stay a certain distance, have a certain tension on those points that are inside the plastic piece. All right? You'll also notice that if you look at the little piece on the left-hand side, that's called a bimetal strip between those 2 points. And you'll notice it's a little bit on the concave side. It's important to note that because that's going to keep those points closed. All right? Again, this is going to be a normally closed switch. And again, that's where the screw goes in so that they can adjust it at the factory. Once they get it adjusted, they put that plastic over it. You can't adjust it after that without voiding the warranty on the motor. Okay? So the next thing we're going to look at here is that little hard wire. You'll see they use aluminum wire right there. Now, they use aluminum wire for a very important reason. The reason is aluminum will get hotter faster than copper does. Now, besides that, aluminum will melt sooner than copper will. And so it's part of the safety device here. It gets hot, it gets the bimetal strip hot, and of course, when that bimetal strip gets hot enough, well, let's take a look at what happens. Okay? When the bimetal strip gets hot, so here's your bimetal strip, your points are touching, they're closed, and the motor's off. Okay, so we turn the motor on, we start running electricity through there. If the electricity going through there gets to be too much, as that aluminum wire heats up, it heats up that bimetal strip, and if it gets too hot, you'll see that it goes from concave to convex, and you wind up popping that open. Now remember, this is a thermal overload protector. Thermal means temperature, and so of course, it's an automatic. In other words, there's no way for you to reset this. Again, this can be important because if you get to the job site and you do an ohmmeter test on this and it's in the open position, you're going to get infinity between number 1 and number 2. Okay? It could be that it's tripped. So you need to wait about 15 or 20 minutes until that thing closes back up again. If in 20 minutes you're still getting it open, then you've got a bad thermal overload. Okay? Because within 20 minutes that should cool down enough to close back up again. Alright? So that's your thermal overload protector. The last thing we want to talk about in this back compartment here is the terminal board. Now, the terminal board that is in the motor right now is probably about 18 years old. All right? The terminal board that's in the little picture there, that one we got rid of about 7 years ago. So, let's take a look because there has to be some similarity in these terminal boards so that we know what we're talking about. All right? This is called L1, and you can see up there you've got L2. This is A, that's B. Now I want you to know there are spades on the bottom of L1, L2, and A, but there is no spade on the bottom of B. All right? Those same features have to be on this other terminal board. So right in there is the way that you're going to use to pick up and move those wires so you can change from 230 to 115. Remember, this is a dual voltage motor. Okay? So if we take a closer look at this, remember now this one's 7 years old, between 7 and 18. Okay? And I also want you to know there's been a couple different designs of this particular type. So this is called the plug-in type. The other one was the wiring. This is called the plug-in type. All right? And when you'll notice here, that black arrow that's on the little black piece that you move has an arrow on it that's pointing to the arrow that says 230 volts. All right? When you move it over, and you'll also notice that there's two spades on L1. Okay? So you do have an L1 and an L2 here, and there's two spades on L1. Right there is where the black wire gets plugged in, and that's plugged into A. All right? So there's a spade there that's called A. Now what we're going to do is we're going to lift this up. We're going to move it over, and we're going to set it down so that the black wire that was on A is now going to be on L1. The black and white wire that was on nothing is now going to be on A. And so we've switched it from 230 to 115. That's the plug-in type. That's the plug-in type. It sometimes can be difficult to see simply because of the fact that while in the picture you see 115 volt or 230 volt in black, in real life that's all white plastic and it doesn't get painted. I did make the suggestion to AO one time that they just run a black roller over there so you could see it easier, and they said, sure, we can do that. How much do you want to pay for it? You can probably tell that was a bad idea, okay? This is what it actually looks like. As a matter of fact, this picture was just sent to me this week. There was a guy who was having some problems, and so I said, well, send me a picture of that so I can see what you're looking at, because I didn't understand what he was looking at. So you can see here, right now, there's the black arrow, and it's pointing to this little arrow right here, and of course you can see that the wire is right over 115 volts. So you can tell that that one is set up so that you're on L1 and you're also on A with the black and white wire. And pictures are worth 1,000 words. I'm telling you right now, anytime you're having a problem, you can't figure it out, send us a picture, because pictures really help us to know what you're doing. I was able to walk this guy through what he wanted to do because he sent me the picture. Without the picture, I'm just guessing at what he's telling me. All right? This is the complete compartment here. All right? And I just want to take a second to walk through all the different colored wires there. So the other important thing to note here is this is the knob type of change. So we had a wiring change, we had a plug-in changer, and now we've got the knob changer. Okay? If you look at the knob, you'll see it's already set at 230 volts. All right? One of the other important things to note here is that L1 and L2 were changed. I don't know why, and when I asked the question, why did you change L1 and L2, the answer was, what? We changed L1 and L2? So there was a lot of people there that didn't realize they'd changed L1 and L2. Of course, they forgot to change their information about how to do testing, and so they had to change that, scramble to change that. That was years before they finally got that changed, but they did get the change made in the book. Of course, now the book is Regal, and they got to change it again, so they've got some things to work on yet. But what you see here is you see the blue wire going into the overload protector. That blue wire hooks up to the bottom of L1, which is now the top L, okay? Then you see the black and white wire there, and the black and white wire comes over, and you'll notice it's going to go over to where the 230 is. It's actually going to be a little bit below where the 230 is, okay? Then there's the yellow wire, and you can see the yellow wire goes down and plugs into one side of that spade, the U-shaped spade in the capacitor, and then there's another yellow wire. That yellow wire goes from the capacitor down to the motor. As long as we're at the capacitor, remember the current's going to go through the capacitor, follow the red and white wire over to the switch, through the switch, and you'll notice there's a red wire on the other side of the switch. And if you look at the top of the capacitor, that red wire is going down into the motor. That's going to go to the start winding. So you've got the yellow wire going down to one of the mains, and you've got the red wire going down to the start. Now the red and yellow wire are going to connect to the black wire, and if you look very, very carefully, it's really hard to see because it's black. The black wire is just on top of that purple wire. And if you look over where the terminal board is, where the black and white wire is, you'll see the black wire sneaks in underneath there, and it's actually plugging in right above the 230. All right? That copper piece that's got a hole in it, that's A. The purple wire hooks up to the bottom of A, so the electricity is going to go through the black wire to the purple wire, and the purple wire goes back down to the second main coil. All right? Now it comes up the white wire, and the white wire comes over, and you see it's hooked up to L2. So while you can see all the wire colors there, and it's kind of neat to see what's going on, it's really kind of difficult to tell. All right? But here's 115 volts, and here's 230 volts. The point that I want to make here, you'll notice, you see that little silver piece right inside there, and I pointed the arrow at it so you can see what I'm talking about. There's another, that's going to be connected to L2. That spade that it's connected to there goes down and connects to L2. Then there's another one over here, and that's going to connect to A. A actually has a spade that goes all the way down to the bottom. We'll see that in just a little bit. Okay? When you're over here on 230 volts, that one that was plugged into A is now moved over to the plastic part, and the one that was on, the one that was on 115 is now on A. All right, so when you go to 230 volt, you're just basically moving those two pieces around. It's important to note that because when electricity hits plastic, what happens? Nothing. Nothing happens unless there's a short, and then you're going to melt the plastic. Okay? But if there's no short, nothing is going to happen. Plastic is an insulator. Remember last time we talked about insulators and conductors. So plastic is an insulator. Now, if we look at this here, this is the bottom side of what we were just looking at. Okay? And again, you can see that purple wire is hooked up to A. There's your black and white wire, and you can see L2 right there. Now, my question is, with this little piece hooked up here, what voltage are we running at? That's going to be 230 volts. That's going to be 230 volts. The black wire is hooked up to the purple wire. That's 230 volts. The white and black wire, you'll notice, is right over here, and so that's going to be going to no place. And at 230 volts, that's what happens. All right? So we're at 230 volts here. Now, again, remember, there are three ways of changing the voltage. There's the terminal winding way of doing it, there's the change plug way of doing it, and there's the change knob way of doing it. All right? We are going from 230 to 115, or 115 back to 230, whichever happens to be. And I want you to know there are some wires on here that are the same no matter what. For example, that blue wire on the winding and the plug change is hooked up to L2. Remember that they switched L1 and L2 when they went to the knob, and so now the blue wire is hooked up to L1. All right? The white wire is going to be hooked up to the other L. And so on the first two, it's hooked up to L1, and on the second one, it's hooked up to L2. You'll see why this is all important in a second. The purple wire is always going to be hooked up to A. It's always going to be on the bottom side of A. All right? Now, there's two wires that can change. The black wire, for example, at 230 volts is going to be hooked up to the top of A. So you can see that in each of these connection types, that black wire is going to be connected to the purple wire. At 230 volts, or excuse me, at 115 volts, the black wire gets moved over to L1. At 230, it's on A. At 115, it's on L1. The white wire with the black tracer at 230 volts is on B. Now remember, B didn't have any other spade connected to it. B was simply there so you could plug that wire in and keep it from getting caught in moving parts. So again, in the plug change type, you'll see it's plugged into the back of that change plug, but it doesn't spin on anything. There's not even a spade there. And, of course, with the knob type, you'll see the black and white wire is touching the plastic because it's not going to conduct electricity. When you go down to 115 volts, now you're taking that white and black wire and you're connecting it to A. So now white and black connects to purple. All right? That still looks a little confusing to you, I can tell. So we're going to actually take a look through the wiring diagram. And we're going to walk through how that electricity moves through this motor. We're using the knob type because that's the most current one. It's been available for the last 7 years, all right? And we're starting out at 230 volts. So at 230 volts, the electricity comes in on L1. Remember, the blue wire is attached to the bottom of L1 and goes over to the overload protector. You might also remember that there is that bimetal strip that connects with points number 1 and number 2. So the electricity is going to go over to number 1 and number 2. Once it gets to number 2, it can move over on the white and black wire to B. Remember, B means it's not really going anyplace, it's just touching the plastic there. Remember also there's a hard wire that connects 2 and 3. So since the electricity can't go any place in the red and white and black wire, it moves over to number 3. Number 3 has the yellow wire on it that takes it down to the capacitor. All right? Remember, it's a U-shaped space there, so most of the current, eventually in 0.3 of a second, all the current is going to go down the yellow wire. But for 0.3 of a second, some of it's going to go through the capacitor and over to the switch. For 0.3 of a second, the switch will be closed, which means it'll go down the red wire through the starting coil or phase. All right? So now it's going to go through the main, through the phase, and it's going to come up on the black wire. Remember, the black wire is connected to A. The bottom of A has the purple wire on it, so now we're going to go down the purple wire. And then, don't forget, in 0.3 of a second, we stop that electricity from going through the phase. And then we're going to come up on the white wire, and we're going to go out L2. All right, so that's 230 volts. When you're running 230 volt, they call it series because you're going through one main coil, then you're going through the second main coil. All right? When I want to run this motor at 115, notice I have to make the change in the knob there. And when I make that change in the knob, what I've done is I've moved the black wire over to L1 and the white wire with the black tracer to A. So once again, my electricity comes in on L1, follows the blue wire over to number 1 in the overload protector. The bimetal strip with the points takes it over to number 2. At number 2, it's going to go the white and black tracer over to purple, which is A, and it's also going to go number 3. Number 3 takes it down the yellow wire. So now we're on the yellow wire and we're on the purple wire. And we're going to go down yellow and down purple at the same time. Remember, for 0.3 of a second, with that switch closed, we're going through phase. The yellow wire is connected to the black, so is the phase. The white wire is connected to the purple. So what happens? We're going to come up the black and white wire, and we're going to disconnect that phase. All right? And then we're going to go out L2. Everybody understand that? Any questions on it? All right. Now, that was the construction of an above-ground motor. Now we're going to take a look at how to start motors, and I want you to understand there are 4 different ways that we're going to talk about today. All right? The first way we're going to talk about is called a split-phase motor. The split-phase motor has a run winding, it has a start winding, and it has a switch or relay connected to it, depending on what kind of motor it is. All right? It can be a submersible 2-wire motor, or it can be an above-ground motor. Now, I will admit, on the pro side, you won't see too many split-phase motor on above grounds. They're used primarily in retail. But if you do have a guy that's working on a retail pump and he says, I don't see a capacitor in here, that's why there's not a capacitor, because it's a split-phase motor. The way that a split-phase motor works, we send electricity in. As the electricity go in, most of it's going to go down the main windings, some of it's going to go down the start windings, okay? it looks a little bit like this as the electricity moves through there. Now remember that start winding is getting hot. And so in 0.3 of a second, that switch or relay is going to open up and stop the flow of electricity through the start winding. And now all the electricity is going to go down that main winding. Okay? Remember when there's movement of electricity, oh, by the way, we're using larger wire for the main. We're using smaller wire for the start winding. Now, there's a reason why we do this. And the reason, of course, is we're putting amps and volts through that wire. As you run amps and volts through smaller wire, the amps go up and the volts go down. And this is why you have to have that relay or switch take that starting coil out of play. Because if it doesn't take the starting coil out of play, you're going to wind up having too many amps there and you're going to burn up that smaller wire. All right? So that's called a split phase motor. It looks a little bit like this. What we're trying to accomplish is something called a phase angle change. All right? Phase angle change. And phase angle change equals rotation. So if we don't get that phase angle change, the motor doesn't rotate. It just hums. And that's why we've got to get that phase angle change. So you can see the starting current pops a little bit before the main winding does, and that's what gets us our rotation. All right? Remember, we looked at this last week, and so again, when you are talking a 4-inch submersible motor, single-phase 2-wire, split-phase motor, what happens? The split-phase motor has a switch that takes the starting windings out of the circuit in 0.3 of a second. Once those starting windings get taken out, what happens? We have a nice smooth pull across these because they've got current going to them. A little rough there, nice and smooth there, and rough there again. And so because we've got this rough in here because we've dropped those coils out, that of course means there's going to be a little bit of vibration, which will get picked up in the pump, and of course it's going to make noise up on the surface. All right? Now, why do we use split-phase motors in 2-wire? Low-cost construction. They are the lowest cost of any motor. Okay? You can run them 1/20th to 1.5 horsepower. Yes, they've been tried at 2 horsepower. No, they couldn't work because of the fact that the current required to start the motor was too much, and they kept burning up those start windings. So it's like, okay, I guess we can't do 2 horsepower. So 1.5 horse is the highest you can go. They are a low starting torque motor. But because of the way that they do start, they are a very high starting amp motor. So we drive those amps up because we're using that smaller wire. All right? We need to limit the number of starts. This is vital. And the reason this is vital is right here. This is out of the PN 793. Franklin has something similar to it. They say the same thing. All right? When you look at it, we're looking at starting frequencies here. We're looking at cycle time. Cycle time means how long from the time I start the motor can I start the motor again. Okay? And you'll notice here that it says if the motor is 1/2 to 3/4, then I can go almost 5 minutes. I have to go 5 minutes between starts. Now that means I'm at about 12 starts an hour or 300 starts in a 24-hour day. Single phase. If I've got 1 through 5 horsepower, which a lot of us use, what are we going to see here? Almost 15 minutes between starts. Almost 15 minutes between starts is what everybody recommends. When I say everybody, I mean Franklin too. They recommend the same thing. If you look in their book, they're going to tell you the same thing. They're going to say 100 starts an hour, which if you do the math, 100 starts an hour comes out to about 1 start every 15 minutes. Okay? The next motor we're going to look at here is called the Cap-Start Induction Run. Cap-Start Induction Run. It's got main windings. It's got start windings, and now we're going to put a switcher relay in there, and that switcher relay is going to be with the starting capacitor in the control box. So while the motor is in the well, the control box is above ground, all right? This is used on submersible 3-wire motors, and I'm going to tell you, most of your jet pumps and sprinkler pumps are also going to be cap start induction run. So you're getting both kinds of motors here, all right? Again, the electricity is going to move this way, and then some of it is going to be drawn off to that capacitor. Remember, it doesn't take a lot of electricity to power that capacitor. And then what's going to happen is, as it goes through the capacitor is going to boost it and send it down to those start windings. So it looks a little bit like this. And you can see you're picking up a boost there at that capacitor. Now again, once you get to about 0.3 of a second, 70% of the running speed, that relay is going to open up and stop the flow of electricity down through those start windings. All right? And once again, it does that because we want to get the big kick. We want to get the big kick. So you can see the big kick here so that we wind up with a rotation. So when we look at a cap start 3-wire motor, okay, it's more costly to construct just because of the fact that you're adding a control box, which is going to have a relay and a capacitor, starting capacitor in there. So it's going to be more expensive. It does, however, operate 1/4 to 3 horsepower on above ground motors and 1/2 to 1 horsepower on submersibles. So submersible motors, 1 horsepower is the highest you're going to get with a cap start. Anything 1.5 horse and larger is going to be cap start, cap run. All right? But you do have a choice with 1/2 through 1 horsepower running them with just a capacitor start. Okay? They're going to have higher starting torque because they're getting their torque through that capacitor. So you're picking up higher starting torque here. Okay? There is lower starting amps than the split phase motor. However, you still got to limit those number of starts because you are putting some amperage through that starting coil. All right? The third method of starting the motor is called permanent split capacitor. It's going to be used on 4-inch submersibles and sump pumps. 4-inch submersibles and sump pumps use what is called a permanent split capacitor motor. With a permanent split capacitor motor, you're going to have a main winding, and again, it's going to be a run or a main winding. This winding you're going to call auxiliary. And the reason you're going to call it an auxiliary winding instead of a start winding is simply because of the fact that you're going to build a run capacitor right in the motor. All right? So now we bring our electricity in. A little bit of it trickles through that run capacitor, and you'll notice we don't get quite as big of a boost through the run capacitor as we do through the starting capacitor. And so it looks a little bit like this, and you can see we got that thing popping there. Okay? Of course, there does come a point where we say, hey, you know what? We're never going to take that out. It's always going to pop. That's why it's called an auxiliary winding instead of a run winding, simply because of the fact that you always keep that winding in play, that auxiliary winding in play. All right? So there's no turning off that capacitor. It's always going to be on. So when we look at that permanent split capacitor 2-wire motor, it uses a run capacitor, not a starting capacitor, so no switch is required. It does go 1/4 to 1.5 horsepower, just like any other 2-wire motor. It has got the lowest starting torque because you're using a run capacitor, not a start capacitor, so you don't get that big kick that the start capacitor gives you. However, you're going to notice it has the highest running torque. And it has the highest running torque because it's got a run capacitor in there. and that run capacitor keeps it kicking all the time. It's got the lowest starting amps because of the fact that it can't go over running amps, okay? And so, of course, we really don't worry too much about the limit of starts. Now, the benefit of having this type of a motor is that it is going to be quieter and it is going to be more efficient than your split phase or cap start motor. So, we've seen 3 motors now, and we've noticed that we get the best starting torque with the cap start motor, but we get the best running torque with the run torque motor, or running capacitor motor. So what if we combine them? Then we would wind up with something called a cap start, cap run motor, all right? Cap start, cap run motor is going to have a main or run winding in it. Again, we're going to call this an auxiliary winding, although we are going to use it during starting also. We're going to put a running capacitor in the control box. We're going to put a starting capacitor in there along with that relay or switch, okay? Now, of course, these are used on 4-inch submersibles and your higher horsepower above ground motors. So when you buy, for example, a 3-horsepower or a 5-horsepower Baldor motor, you will notice that they have a capacitor built in on the top of the motor. That happens to be your running capacitor. Once again, we turn the electric on. Most of the electric's going to go that way. We're going to pull some off. Notice we're pulling just a little off to go to the run capacitor, pull a little bit more off to go to the starting capacitor, and of course that means we're getting a big boost through the starting capacitor and a smaller boost through the running capacitor. Okay? So it looks a little bit like this when you get it moving. Of course, remember, in 0.3 of a second, that switch or relay is going to open up and stop the flow of electricity through the running or through the starting capacitor. However, we still have the flow of electricity through the running capacitor, and because we do, that means we're using all these coils all the time. So we are going to pick up the benefits of both worlds. We've got the best motor right here. Okay? Cap start, cap run. Remember, this is single phase. So in the single phase world, this is the best. It is the most costly because you've added both a start and a running capacitor to it. Now you can go half through 5 horsepower in 4-inch and 5 through 15 horsepower in 6-inch. 15 horsepower is the highest submersible motor they make. Okay? It's got the highest starting torque and the highest running torque because you've got a start and run capacitor in there. Lower starting amps in the split phase, but again, you need to watch the number of starts because you've got that starting capacitor in there. That's what's giving you your starting torque. So you kind of have to watch those number of starts a little bit. Okay? It is going to be quieter and more efficient than the split phase or the cap start motor. Now again, we've looked at 2 different types of motors here. We've looked at a 2-wire motor and we've looked at a 3-wire motor. If you're running a 3-wire half through 1 horsepower, you have a choice between control boxes. All right? So here's the 3 control boxes that we sell. This one here is the SMC-IR. And remember, you can run half through 1 horsepower with induction run, cap start induction run. And that's what this is. Okay? This box here is the SMC-CR. SMC-CR goes half through 5 horsepower, and now you've got a starting capacitor and maybe 1 or 2 running capacitors depending on the horsepower of it. Okay? But it does work half through 5 horsepower. And then, of course, the one in the back there is the SMC-CRP, and that runs 2 through 5 horsepower. Now, let's talk about the differences in them. The IR box only has a starting capacitor in it. Nothing else. Well, a relay. But as far as capacitors are concerned, there's only a starting capacitor in there. When you go to the CR box, now you've added a start and run capacitor. What makes the CRP the plus box it has the run and start capacitors with a magnetic contactor, and I'll tell you what, that's what I quite often recommend when it comes to hooking up control boxes, okay? So when we look at our control boxes here, the bottom one is your CSIR, the top one is your CSCR. Let's look at the IR box first. We come in on L1, go right down that black wire to the main in the motor, okay? We pull some of that electric off, we run it into the capacitor. Then we're going to go through the capacitor and come up on the orange wire and go over the relay. There is a normally closed switch. Because the switch is closed, the electric is going to go down the red wire. And so now we go down red, down black, up yellow. Once yellow has reached number 5 there in the relay, it winds up, once I get enough voltage there, that you open up the relay and stop the flow of electricity from the starting capacitor. So now you're only using the main windings again, all right? When you go to cap start cap run, L1 comes in, goes down to the main and to the start capacitor. Now remember that start capacitor has a U-shaped spade, so part of the electricity is going to go from the U-shaped spade over to the run capacitor, and then from the run capacitor down the red wire. The other part is going to go into that start capacitor, follow the orange wire over the relay. Remember, the relay has a normally closed switch, so it sends its current down through that red wire. We go down red, we go down black, we come up yellow. Once the current at the relay, once the voltage at the relay reaches what it's supposed to be, it opens up and stops the flow of electricity from the starting capacitor. Now you're only pulling current through the running capacitor. But you're hitting on all 18 slots. All right? This is a typical pressure switch. You'll notice there's 2 wires coming in from L1 and L2 on your disconnect switch and 2 wires going out to your motor. The other side has two connecting to this one and 2 connecting to that one, so that you can see there are 2 sides there. All right? When the pressure drops, this is across the line starting, when the pressure drops, that closes. Now watch the flow of electricity. All right? So you've completed the circuit and you've got the flow of electricity there. Again, all this happens in about 0.3 of a second, or 2415 RPMs. When we go, and this is a picture of the 2 3/4 plus box, when you go to the plus box, remember, you're building in a line contactor in that box. So L2 goes up to L2 on the contactor. We also pull it out of the box and take it over to the pressure switch. L1 comes in, goes through the main overload, and up to L1 on the contactor. Then there's a little wire that's pulled off of L1 that goes to the side of the contactor and connects part of that magnet. Now, without the other side being connected, there is no magnet here. All right? Once the pressure switch closes, now the electricity flows from L2 up to that other side of the line contactor magnet. Once we magnetize, now we close the contactor and we connect L1 to T1 and L2 to T2. We'll come out of T1 first, and when we come out of T1, there's 1 black wire that goes right down to the motor. The other black wire, now watch this because it's a long run. The other black wire comes over, goes to the starting overload, up to the run capacitor, follows the U-shaped spade over the starting capacitor. Now it's going to go down through the run capacitor and put electricity on that red wire. It's going to go down through the starting capacitor, send the current over to the relay. Remember, the switch is normally closed, so that's going to go down the red wire too. So now we're going to go down red, down black, come up yellow. You'll notice yellow is connected to T2, but there's also another jumper that goes over the relay. And of course, when the voltage is correct, it opens up the relay and stops the flow of current from the starting capacitor down to that motor. Remember, you're going to hook it up to the pressure switch. Now, of course, what you're going to do this time is you've got L2, which goes from the terminal board to of the plus control box. If you have a qualified electrician, he's going to want you to connect SW there because he knows you're supposed to use the two outside wires. Okay? Of course, now you got to get the connection from here to here, because when this closes, watch your flow of electricity now. Okay? Of course, that's not the best way to do it. All right? The best way to do it is right here. That way, when you get that flow of electricity, if something happens to that set of points, you can always move your wires over the other set of points, and now you've got another set of points to use. Okay? 4-inch motors, 1/2 through 5 horsepower in single phase. You can buy a 1/2 horsepower motor as 115 volt or 230. Now, unlike its above ground counterpart, the 4-inch submersible motor is either wired 115 only or 230 only. So you have to pick the right motor for the voltage that you're using. If you hook up the wrong voltage to the motor, if you're putting 230 to 115, you're going to smoke the 115 motor. If you hook 115 to 230, you're going to be tripping that overload all the time. Okay? 6-inch motors, single phase, are 5 to 15 horsepower. Got a question for you. What are the advantages of 230 volt? Well, let's take a look here. We're going to talk about power consumption because, of course, some people believe that it costs less to run a 230 volt than a 115 volt motor. Is that true? We're going to see in a second here. Some people believe that the 230 volt motor runs cooler than the 115. Doesn't draw as many amps, can't run as hot, right? And of course, some people believe that a 230 volt motor is more efficient than a 115. Let's see how true that is too. So we're going to start out by saying that this 115 volt motor draws 14.8 amps. Remember, when you're buying electricity, you're paying for watts, in particular kilowatts. In this case, you're going to have 1702 or 1.7 kilowatts. All right? If I run that same motor at 230 volt, it's only going to draw 7.4 amps, so therefore it must be less watts, and the answer is no, it's not. So, is it true that you save money on electrical costs running 230 volts and 115? And the answer, of course, is no, it isn't. Okay? Is it cooler? Well, how many overload protectors are in that above ground motor? 1. So if there's only one overload protector, it's protected. Doesn't matter whether it's 115 or 230. Now, let's take a look at, and this is out of the PN 793, let's take a look at the efficiency of the motor. So we're going to compare here, and we're looking at efficiency. It's going to talk about full load efficiency and service factory efficiency. All right? We're going to look at the 2-wire motor first, and we look at the 2-wire motor, and then we got the 3-wire motor down here. We're using CSIR. The reason for that is they don't make a CSCR 115 box, so we have to use CSIR. Okay? You're going to notice on that 2-wire motor that, yes, indeed, the 230 volt motor is about 3% more efficient at full load than the 115, and it's about 4.5% more efficient at service factory. However, if you go to the CSIR, now you'll notice the 115 is 5% more efficient at full load, and it's about 4.5% more efficient at 3.5% more efficient at service factor load. So the question is it really enough to say yes, that changing to 115